So,
yes, CRM, we can now hear you.
oh, good. Yeah. So, yeah. So what we saw last time is that the flow table constructed with the assumption that you have only one of the inputs can change at a time. So according to that assumption, the flow table can be constructed. And once the flow table has been constructed, it can be treated just as an incompletely specified finite state machine, and then state reduction can be carried out. Okay, so for this particular machine, uh, this is the merger graph, and accordingly you can have these realizations. Again, these are symbolic realizations, but as we shall see, this is not the end of it. So we have to be careful about something that we call hazards. Okay, so so we'll be studying hazards. I mean, I mean separately, but through this. So let me just. So the concept of a glitch. Okay, the concept of a glitch. So let us say that your output, I mean, your output, say there's a 0 level and there's the 1 level. So suppose your output is supposed to be 0, but for some reason it can just rise up and then again fall. I mean, this uh, this is usually a very short span, maybe 1 nanosecond, or maybe you know 1 nano, maybe even less than 1 nanosecond. I mean this, uh, or it may be the other way around. So it may be one. It might have a very short. So these are usually not visible to the eye, but these changes. I mean, obviously, if it is for a duration of 1 nanosecond, you are not going to see it very easily. But I mean, it is possible to, so you have in your lab, although you have not used it, you have got this CROs or cathode ray oscilloscope. Okay, so have you used the CRTs or CROs? Have you used them in your basic electronic lab, for example? Hello? Yeah, can you answer me? Someone. Have you used this CRO anytime?
No, sir.
No, you should use them. So, I mean, this is not a graded assignment. Oh, by the way, I hope you are aware that I mean I had posted also an assignment has been put up in WBCM. So now that you are also attending the lab physically, you should do certain experiments. I mean, in the lab, the online experiments will go on as usual, but you will get to do a few things in the lab to get an understanding of using hardware and becoming more familiar with signals. So this is an exercise, or okay, I mean. You study what is called study the working of a chatterless switch. It's also called a debouncing switch. So what happens is, I mean, you have studied the usual symbol of a switch. Sometimes you might also have a sure handle. So this is a switch. So this could be open or it could be closed. So when it is closed, so usually this will have a little contact here. So you might have a contact here also. I mean, this more the symbol of a switch is very straightforward, but I'm just showing it a little more graphically. So you can have a contact here, and this is how this is open. This is open, and here the switch is closed. All right, here the switch is closed. Now, what happens is, I mean, if you assume that this is at logic 1, and this, well, just this is called a passive pull down. Because if you leave it floating, it could be at some arbitrary voltage. So this is a high resistance. So high resistance meaning so when the switch is closed, almost no current will flow through this resistance. Okay, so this I is nearly zero. Okay. Let me. So here, I is nearly zero. So if you now watch this on a CRO, so let us call this, this voltage V. Voltage here is V. So when the switch is open, so I mean, let us say that 0 is 0 volts, and say 1 is something like 5 volts. All right. So when the switch is open, it is at 0 volt. Now, when you try to close it, it's not so neat because it will touch it, it will open it. So initially, what happens is, say it will rise, again it will fall, again it will rise, again it will fall. This will keep on happening for some time. Ultimately, it will, become steady. So this phenomena is called chatter. This phenomena is called chatter. Okay, and this can be very harmful. I mean, this chattering essentially means that you're giving a large number of inputs. Just a minute. You're giving a large number of inputs to your you're giving a large number of inputs to your system. So effectively what it means is that you may not even know the current state of your system. Okay, you may not know the current state of your system. So that's a very dangerous thing, and if you're, operating a safety critical software, some very undesirable outcome, you might have to face some very undesirable outcomes, especially if your finite state machine is part of a safety critical system. So one way is to avoid that chatter. Okay, so actually you have already learned enough to to avoid that chatter. So what you have seen is that, can anyone tell me? Can anyone tell me? You have already studied this in the class. The working of a flip flop. So the working of a latch. This, I mean, that time we did not specifically mention chatter, but can anyone tell me how you can remove this chatter? So I've already given you the hint. You make use of a latch. So can anyone suggest how you can use a latch to avoid this chatter? Yeah. Anyone would like to answer? I mean, why don't you try? Maybe I can ask someone who is present. Can yeah, of course. Maybe those of you who are in the class, you may not be you may not be showing up here. So anyway, I'll just ask someone who is there who is showing up here. So Shoptoshi De. Shoptoshi, are you there? Hello? Shoptoshi, are you there? Well, apparently no. Munish, are you there? Manish? Hello? Anand, are you there? Anand?
Yes, sir. Yes, sir.
Yeah, so would you like to try to answer this question? Did you get the question? I mean, we are discussing this chattering, which is
Yes, sir.
shown. So, do you have any suggestions how you can avoid this chattering using a latch?
Uh, sir, I'm thinking about it.
Okay, so is anyone ready with an answer? Yes? Well, let us try to draw the. So I hope you can draw the circuit of a latch. Why don't you draw it in your notebooks? Why don't you draw it in your notebooks? So this is the basic circuit you have. All right. Let us call it Q. Let's call this Q bar. All right, and then you have well, you could just well, let us just keep it like this. We can sometimes call this enable. So Well, if it is zero, it is not enabled, right? If it is, see, if enable is zero, enable is zero, enable is one, then what happens? So suppose you make this zero, okay? Suppose you, okay, let us call this, set S and R, okay? So S equal to 0, S equal to 0, is this one becomes 1, okay? So this one is, well, if this is 1 and this is 1, if this is 1 and this is 1, sorry, S equal to 1, okay? If S is 1, then this becomes 0, okay? And if this becomes 0, then, okay, so let me just change it. I'll call this one S and this one R. Yeah. So this one is S and this one is R. All right. So so if I make S 1, so when S is 1, this one becomes 0, right? When this one becomes 0, so this one is Q is equal to 1. And so S1 0, S1 is 1, and R is 0. R is 0. And if you make S equal to 0 and R equal to 1, then what happens? Then Q, you can say, is equal to 0. Okay. So this is how it works. All right. This is how it works. Now, of course, as you have noticed, normally, if you leave a terminal floating, that takes the logic value 1. So if you have to keep this as 0, so default. What is the default? Default is default is S equal to 0 and R is equal to 0. That is the default, right? So yeah, that's the default. So what you do is, if you wish to achieve that, a good way is to have this passive pull down. So you have this passive pull down. This is a passive pull down. And the other way, so do you understand this? How this is working? So now what you see is you don't have any chattering. So if you want to, so if you set S to 0, this will go to 1 and there won't be any chattering. All right. So there won't be any chattering. So once you so so even if there is chattering at S, there will be no chattering at Q. That is the point. All right. There is no chattering at Q. So can you suggest a solution without the passive pull down resistors?
So we can connect a NOT gate between inputs S and R. Then it
Yes,
will be a D latch.
you can do that. You can do that. So and another option is to use a latch with NOR gates instead of NAND gates, right? You can use a NOT gate, of course, but another option is to use a latch with NOR gates instead of NAND gates. All right. So that can be done. So this is about about this chattering, okay, and how you can avoid chattering. So how you can avoid chattering. Now let us come back to our the topic that we were looking at. So now here um, here let us. So what you saw here, I mean, you're familiar with this part. You have already done this state minimization for incompletely specified finite state machines. Okay, so this part is you're already familiar with. But now let us see something that you need to be careful about when you are designing asynchronous circuits. So first of all, let us see the effect of state assignment. So as you have already seen that you got to assign some states, some values for the symbolic states. Okay, that's called state assignment. You got to assign certain bit values. So uh, so you can so here uh, we are okay. We are not considering this machine immediately. We are considering another machine, okay, which is shown over here. All right. So we will. Okay, so here what I have said is any choice. Let us just read. So two possible margins have been depicted. The output mark. Yeah, the outputs marked red. Okay, yeah. So yeah, so here also there is something to be careful about. Okay, let us just see. So if you remember that this part was not specified actually. If you march the states, these things in red, these are essentially these are still don't care. I mean, you have the option to assign this either 0 or 1. Now when you make this assignment, it is always better to choose this as the stable output, because otherwise what can happen, I mean, the stable output is 0. Okay. Now, when you are when you are in a different state, well, in this particular case, whenever you are in beta, the output is 0. Okay. So let us consider this thing. So here, let us say the stable output is 0. Okay. When you're in alpha, the stable output is 0. Now, as the input changes from 0, 0 to 1, 0, you are making a transition to beta. Now, this output is undefined. Okay. So just see what is happening. I'm just. So your input is, so this is a time axis. Your input is say 0, 0 now, and your and then as I was saying, it is changing to 1, 0. Okay, it's changing to 1, 0. So what is the output? Output. So you know that your stable output for say your state is alpha. Okay, your state is alpha. So so you're in state alpha, and now you're going to state beta. So in alpha for 0, 0, the stable output is 0, and then here also okay, I mean, let us just draw it like this. Let's just bring it a bit closer. Okay, so here now here also your output is 0, but you had the option to keep it 1. So if you keep that stable output as 1, over here, that is over here, if you keep that stable that unstable output as 1, then you get a glitch. Okay, which is, you don't want this. So that's why it's better to keep the output as 0. So you keep the output as a stable output of that state. The stable output of beta is 0. So better to leave it at 0. So, uh, yeah, so you directly go to the stable output. You don't have these glitches. So it is important to, so when you're setting the output, when you're setting the don't care value of the output, you should be careful to set that to a value which will avoid glitches. Okay, that is an important aspect to consider. I mean, this, of course, this consideration is also there to some extent when you design synchronous circuits, but we will see. We'll see. We'll look at that when we study hazards separately. Okay. So in the context of asynchronous design, what you can see is that you have to be careful when you decide upon when you set the value of this don't cares. Okay, so that is one part. Now let us look at this machine. So again, I mean, this is again a symbolic symbolic transition. So let us see what is happening. Okay, let us just see what is happening. Okay, so here you you have got 4 states: S0, S1, S2, S3, and as you can see, here I think I have sort of S0, it's stable. Yeah, so the output of S0 is not specified though. Let us just say it's yeah. So anyway, the stable it is stable for 0, 1 input. So you can see that all of these are self loops. So this self loops indicate the stable value. So S0 is stable for 0, 1, S1 is stable for 1, 0, S3 is stable for 0, 0, S2 is stable for 0, 1. Okay, so yeah, all incoming transactions are on. Yeah. Okay, so here what you're seeing is that the incoming transitions, okay, the incoming transitions are also on 0, 1. So here, as you can see, the incoming transitions are also on 0, 1. Here in state 2 also, the incoming transition in S1 the incoming transition is 1, 0. In S2, okay. Oh, I see. Sorry. Here it is okay. Here I should have used a comma perhaps. I think I'll have to change the notation. It should be a comma. Yeah. So it's not an output. These are S3 is stable for 0, 0 and 1, 0. So I'll have to correct this notation. It is stable for 0, 0 and 1, 0. It should be a comma rather than a slash. All right. So yeah, so S2 is stable for 0, 1 and 1, 1. And the only incoming transition, as you can see, oh, sorry, this is S3. So S2 is stable for 0, 1 and 1, 1. And the only incoming transition is for 1, 1. And S3 is stable for 0, 0 and 1, 0. And incoming transitions are on 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1. Now, it is yeah, so it is unstable for 1, 1 input, and when the input say from 1, 0, if it changes to 1, 1, we are still with the single input change model. So from 1, 0, if it changes to 1, 1, it goes to S2. Okay, so now yeah, so we are immediately apparently not considering any. Yeah, so here I put comma, there I put. Okay, so now we are considering some state encodings. Okay, we are considering some state encodings. So state encoding, so you have got states S0, S1, S2, and S3. These are symbolic states, and we are considering certain encodings. So 0, 0. So encoding for S0 is 0, 0, encoding for S1 is 0, 1, encoding for S2 is 1, 1, and encoding for S3 is 1, 0. Okay, so so now let us just see. So S2, so let us look at S2. S2 is here. Okay, so S2 is encoded as 1, 1. On getting 0, 0 or 1, 0, it makes a transition to S3. So on getting 0, 0 or 1, 0 as shown over here, it makes a transition um, to S3. And when it makes this transition, now this is the important part, okay? This is the important part. So you're having only one input change. So this encoding for S2 is 1, 1, and the encoding for S3 is 1, 0. So you're having only one input change, okay? So this is changing from 1 to 0. This one doesn't change. This one doesn't change. We'll see the importance of that. So let us. So you have look at S3. S3 is encoded as 1, 0. On getting 1, 1, it makes a transition to S2 with one input change. So here, if the input changes to 1, 1, it makes a transition to S2 where you have just one input change as before. So this is the sorry, one change in the state. So and similarly, if you get 0, 1, it makes a transition to 0, 0. So uh, uh, there also only one bit is changing from 1 to 0. Okay. So this single bit transitions are okay. So I think this you will understand. Okay. This is also a similar thing. Now let us look at what is happening in S1. Okay. So so let us see what happens here. So S1, it is encoded as 0, 1. Okay. It is encoded as 0, 1. S1 is encoded as 0, 1. So on getting 0, 0, it makes a transition. On getting 0, 0, it makes a transition to S3, okay, with 2-bit changes. So let us see. S1 is encoded as 0, 1 and S3 is encoded as 1, 0. And on getting 0, 0, it makes us, or for that matter, 1, 1, it makes a transition to S3, okay? It makes a transition to S3, but there are 2-bit changes, okay? So there are 2-bit changes. Now, we say that further investigation is needed. Why? Because, see, in practice, when you are changing from, you know, let us say 0, 1, okay, 0, 1, you are changing to 1, 0. So actually what happens is this one will change to, let us say, so this one could change to first 0, 0, okay. This one could first change to 0, 0. Let me just put it here. It will first, let us say, change to 0, 0. Okay, there's the actual change that will happen. And then, okay, so again, I did not have really put it there. It will change to 0, 0, let us say. And then this 0, 0 changes to 1, 0. So, because your circuits, your assumption is that your circuits all don't operate at the same, exactly at the same speed. There will be some minor changes, some small differences. So these 2 bits will not change exactly at the same time. So first, this is changing to 0, 0, or it could also change the other way. It could also change to 1, 1, and then it could change to 1, 0. Okay. So these possibilities, so you have to assume that this is what is going to happen. So let us see what happens. So suppose 0, 1 is changing to 0, 0 first. Okay. 0, 1 is changing to 0, 0. All right. So effectively it is making a transition to S0. But so this is on 0, 1. But the good thing is that on 0, 1, okay, if you have the single input change from 0, 0 to 0, 1, it goes to S3 anyway. All right. So you wanted this transition on 0, 0 to S3, but you might on 0, 0, it might actually come here. Okay, it might actually come here, because as you have seen, the state change doesn't happen in one go. It might change to 0, 0. But from 0, 0 also, you find that it, the transition is to S3. It's all right. Okay. Now let us see what happens in the other case. So say, as you said, it can also change to 1, 1. So this is 1, 1. So if it changes, so this is shown in on input 0, 0, it can come here, but here also on 0, 0, the transition is back to S3. So it's still all right. Okay, you're going to have your desired transition. You're going to have your desired transition, even if it you're actually following this path. But see what happens here. If you get 1, 1, okay, so this is the important part. We are basically at the end of the class, but I think we can just see at least one. So if you suppose you get 1, 1, okay, so on getting 1, 1, so here also on 1, 1 also you have this change from 0, 1 to 1, 0. So let us see what happens. I mean, suppose you just instead of going to 1, 0, you could you could have this transition. First, it changes to 1, 1. Okay, you first you have this situation where your the state is changing to 1, 1. So that means you are coming here. Okay, you're coming here, right? You're coming here. Now. But over here, what is happening is that this state is stable for 1, 1, so it will get stuck here. Okay, you wanted it to come here, but because this 0, 1 is not changing to 1, 0 in one go, it is say changing to 1, 1. You come here, but now for S2, as you can see, 1, 1 is a stable input, so it will get stuck here. So you will not have this transition which you wanted. All right. So I think we'll stop here now, but I just, so we'll continue from here, but I hope you have understood the basic problem. So state encoding and, these things matter. So we have a problem, and we'll investigate this. We'll investigate this problem further in the next class. So let us stop here now. Okay.
Thank you. Thank you, sir.
Yeah. Thanks. Okay. So I think the recording has to be stopped.